Okay. Hello, everyone. Thanks for coming to the NetPlay seminar for this week. And today, we're very glad to have Professor Giacomo Lieven here to give a talk. So Professor Giacomo Lieven is associate professor at the Department of Computer Science of University College London, and he mainly working on the emergent behavior of socio-economic systems. So today, he's going to talk about leveraging bibliometric data to understand academic impact. So thank you very much, and the time is yours.
All right. Thank you very much. Thank you, Annalisa. Thank you, Anlene. And thanks, Gabriele, who told me he was not going to be able to make it. Thanks a lot for inviting me. It's nice to get to give a seminar here. So yeah, like my seminar says, what I want to talk about today is scientific impact. So essentially what makes scientific publications impactful, and seeing whether we can figure that out based on bibliometric data. So that's essentially data, all sorts of data about scientific publications. So given that I would like not to take too much time and leave ample time for questions and discussions, I'll cut to the chase, essentially. So basically, this is the broad research area where this talk is placed. So bibliometrics was in my title as well, and that's the statistical analysis of basically all sorts of data that pertain to academic publications, and this partially overlaps with scientometrics, which my research touches upon as well, which is essentially the discipline that seeks to study the development of science, technology, and innovation, and that typically happens through the analysis of scientific publications. So that's why there's an overlap. And I guess you're very much familiar with the names you see here. So this slide is essentially to convey the idea that in recent years, both fields, scientometrics and bibliometrics, have witnessed an increased availability of data sources from all sorts of platforms. So this has opened up a number of research opportunities. It has made things relatively easier in terms of access to interesting data. And this is why a lot of people now coming from all sorts of disciplines are getting interested in these fields. Like I myself I am a physicist by training, and I am in a computer science department. And this is a very interdisciplinary community. And in fact, like this is just, again, to give you an idea, in a few years ago, there was a review that came out in Science titled Science of Science, which is like, let's say, a rebranding of these fields I have been mentioning. And you can see here the names of a number of top scientists that got involved in this area. And if you read this review and other reviews that talk about the science of science, you see that they basically cover let's say, this very non-exhaustive list of subjects, plus many more. So for instance, they look at how academics form social networks and how these lead to collaborations or to the impact of their publication. They try to predict success. They take a look at career trajectories, how funding is allocated, and so on and so forth. And like I said, all of these topics, all of these questions can now be asked and tackled much better than just a few years ago, thanks to the increased availability in data. And I guess before I tell you about my specific research question and what I would like to talk about today, I guess there's an overarching question, which is, why do we care about science of science, bibliometrics, etc.? Well, I would say the reason we care is basically because so-called bibliometric indicators, so these are the indicators that tell us how impactful publications are. So first of all, citations, but then, there's a bunch of indicators that can be derived from crude citations, such as the H-index and so on and so forth. So it depends on the academic system, it depends on the country, but all of these bibliometric indicators nowadays influence all aspects of academic decision-making in one way or another. So they may determine whether you're hired, whether you're promoted, how likely you are to attract funding, how likely you are to form certain collaborations. And in certain countries, there are even salary premia that are tied to academic performance as measured in terms of bibliometric indicators. So at the end of the day, this is a very controversial subject, whether measuring academic impact with these indicators is a good idea or not. I'll try to offer some thoughts on that, but I would say undeniably, this is how things are done these days, and that's why I think we should care. Meaning figuring out what determines the evolution of bibliometric indicators is important for the reasons listed here and many more. So having said that, let me cut to the chase and tell you basically what I would like to talk about today. So given that I've been told that the audience is made most likely of early career researchers, I thought it could be interesting to take a look at a couple of papers of mine that basically try to look at the, let's say, prediction of academic impact in the long term by looking at early careers. So, and how they evolve over time. So in both papers, we'll take a look at a bunch of people in different disciplines that had long-lived careers. So they published for decades. So then we go back in time, take a look at the origins of their careers and see what happened throughout the development of their careers. So I will start from a perhaps provocative research question, which is whether academic success can be inherited, and I will clarify what I mean by that in a second. And then I will instead look at, let's say, individual disciplines, and we'll take a look at the relationship between the inequality in a discipline, as in how, let's say, concentrated the distribution of citations is in a given discipline across the people who publish in that discipline, and how that relates to the mobility in that discipline, where mobility means how likely or unlikely you are to climb the ranks of your discipline given, let's say, your initial conditions, the initial conditions of your career. So let me start with the first one. So here, what we want to see is, like I said, whether success can be inherited, academic success can be inherited. There is quite a vast literature that takes a look at the relationship between mentors and mentees. And that has established a number of findings, meaning that there is evidence that, of course, mentors have an impact on their mentees. And having, let's say, mentors that are highly impactful themselves or have published highly cited research or highly visible research, of course, has a beneficial effect. In this paper, we wanted to basically take this research to its extreme consequences and see whether just co-authoring a single paper, or at least a single paper, early on in your career with a top cited scientist in your field can have career-changing consequences. So just to give you a flavor of the data and of context, here we are taking a look at 4 disciplines, STEM disciplines, and in general, we tend to look at STEM disciplines in this kind of papers because humanities, social sciences are pretty different in terms of publication culture, frequency of publications, etc. So here we look at cell biology, chemistry, neuroscience, and physics. And here we take a look, like I said, at a number of scientists in these 4 fields who had long-lived careers, so at least 20 years of, let's say there's at least 20 years of recorded publications. So people who definitely didn't just have an early career, but just went on and published for at least 20 years. And overall, with a few restrictions, so we want people with at least 10 publications and at least 1 paper published every 5 years. So we are sure that they are at least a little bit active throughout those 20 plus years. Overall, that gives us a sample of more than 22,000 scientists across the 5 disciplines. And then just to clarify the vocabulary that I'm going to be using in this first half. So I'm going to I'm going to call a junior researcher someone who is in the first 3 years of their career, which means the first 3 years after the first recorded publication. So most likely that's someone who is a PhD student or in between PhD and postdoc. Then I'm going to refer as a top scientist, quote unquote, in the field, in each of the 4 fields, as someone who in a given year is in the top 5% in terms of received citations for that year. It's an extremely stable indicator. So typically, if you become if you enter the top 5% of a field, you typically remain there for many years until basically you retire. I should clarify here that this is just, you know, a nickname, a shortcut. So top scientist here means top cited, but by no means I want to say that you cannot be a top scientist unless you are in the top 5% or whatever percent in your field. And then I'm not going to go into the details here, but we have, I'm happy to talk about it later if you're interested. We have a proxy for institutional prestige. So we have the affiliations of these authors. And using this nature index, we are able to compute essentially a proxy for the institutional prestige. So the prestige of an institution that people may be affiliated with. We check that against like many of the standard rankings. And of course, at the top of this institutional prestige ranking, you find some of the usual suspects, I don't know, Harvard University, and so on and so forth. So this is the first picture that basically already gives you a feeling of our main result here. So here is our group of 22,000+ authors across the 4 disciplines. And here we basically split them into 3 groups. So the people in blue are those who don't have a paper published with a top scientist in the first 3 years of their career. The group in orange, labeled as single, are those who have just 1 paper with the top cited scientist in the first 3 years. And those labeled as multiple are those that have more than 1 paper like that. It could be with the same person, the same co-author, or another co-author. And again, here we don't care at all whether this co-author is a mentor or some kind of, similar figure. It is just a co-author. So like I said, we want to take this kind of literature to its extreme consequences. So on the left here, you see as a function of this distribution, the percentiles of the institutional prestige distribution, the number of people in each group. So of course, let's say the people who don't get to publish who don't get to publish papers with top scientists in their field are the majority. So you see here, this is in log scale. And then you see that the other 2 groups are the minority, and there is some positive correlation, as you would expect with institutional prestige. So the higher the prestige, the more likely you are to publish with top-cited scientists. The plot on the right, though, basically summarizes the main result, and then we'll look at it in a bit more detail. So on the y-axis here is the probability that one of our early career researchers has become a top-cited scientist themselves at the 20th year career mark. So we basically look at the first 3 years, see if they have 1 or more papers with a top scientist, then ignore what happens and go to the 20th year and see if they have become a top-cited scientist themselves. As you see, for each group, there is some positive correlation with institutional prestige, but I guess the main point here is that no matter the level of institutional prestige, if you do publish 1 or more papers with a top-cited scientist in the first 3 years, this gives you a clear competitive advantage, and it's a pretty strong predictor of whether you yourself will become a top scientist in your field. So this is a very macro perspective. Now let's break it down a bit more to see how this happens at different levels of early career success, so to speak. So you see here that there are some labels here on the x-axis with letters. So here we are basically splitting our 22,000 authors into into mutually exclusive groups based on early career indicators of success. So I means you're in the top 5% in terms of institutional prestige early on in your career, so compared with other early career researchers. P means you're in the top 5% in terms of early career productivity, and C means being in the top 5% in terms of early career citations. Now, IP, IC, PC, IPC means that you are in the top 5% in 2 or all 3 of these categories. and in a mutually exclusive way. So if you are in this group, in the top 5% of IP, you are only counted here and neither in I or P. And the group labeled as none, which is of course by far the most numerous group, are people who are, let's say, who are not in the top 5% in none of the three dimensions. And here, for each of these groups, we are comparing the probability of becoming a top-cited scientist at the 20th career year. And we do that for the yes and no groups. So those that do have a paper with a top-cited scientist in the first 3 career years, those are the yes group in brown, and those who don't, who are in purple. So you see that if we start from the right, so the people who start their career with in the best possible scenario, so they are at the very top in terms of institutional prestige, productivity, and citation, having this kind of collaboration early on, this kind of co-authorship doesn't make a difference. This is perfectly equivalent. Whereas if you go down, let's say from right to left, you see that the probability of becoming a top scientist decreases in absolute terms. But the interesting thing is, if you look here, this is where you have the highest relative difference. So if you, let's say, do not start your career in one of these, early successful groups, this is where you have the biggest difference. So having a paper published with a top co-author basically doubles the chances for you to become a top-cited scientist yourself. So this number basically doubles from roughly, this is 17 or something % to more than 25. So then we want to investigate this even better. And here what we did is we applied a method called pair matching. So we wanted to basically do what people usually do in clinical trials when they want to test the effectiveness of a new drug, or say like a vaccine. So what you do in clinical trials, you typically form a treatment and a control group, and you give people in the treatment group the vaccine or the drug, and people in the control group a placebo. However, you don't want to form these two groups at random, because then by chance you may have a bunch of people with pre-existing conditions ending up in one of the two groups, and that may bias the results. So what you want to do is to find pairs of people with that are identical or as close as possible across a list of features. So in the case of clinical trials, that may be, I don't know, body mass index, whether the person is a smoker or not, eating habits, and so on and so forth. And then you send one member of the pair to one group and the other member to the other group. So that allows you to basically remove all possible biases and all possible confounding factors. So here we did exactly the same. So we found pairs of early career scientists in our pool that had almost identical profiles, early career profiles, in terms of the 3 dimensions I have referred to. So early citations, productivity, and institutional prestige. And then basically our equivalent of, let's say, giving a vaccine to one of the two is basically having this difference. So one of the 2 members of the pairs has an early career paper with a top scientist in the first 3 career years. The other member of the pair doesn't. Then, I will spare you the huge table. And again, this is just to show you that we have done our homework, but there's no need to look at all these numbers. Basically, what you do here is, after forming these 2 groups, you look at a bunch of dimensions, and then if there are differences across these dimensions in the 2 groups, then you can conclude that your results are statistically significant at the level of individuals here. So again, this is equivalent to claiming that a certain vaccine is effective after doing this kind of control at the level of pairs. And so what we did after forming these 2 groups in each disciplines, here for instance, you see cell biology, is we checked these 5 dimensions here. We checked for differences across the 2 groups in these 5 dimensions. So the citations received over a certain period of time. So across all the first 20 career years, after the first 3, the citations per paper received after year 3, the number of co-authors top co-authors, I should say. So how many times people got to publish with other top-cited scientists after the first 3 years, both in terms of number of top co-authors or number of co-authorships with this kind of people. And invariably in each discipline and in each of these 5 dimensions, we found that the group, let's say the treatment group, so the people who got to publish early on in their career with top cited scientists had, for them, these numbers were systematically higher. So they did have a systematic competitive advantage throughout the rest of their career. So what are the conclusions, let's say, of this first part? So here you could say that there's a chicken and egg problem. So what we may be seeing is option 1. So it's the collaboration with top scientists that leads to greater success or greater impact. Or option 2 is that instead, due to early career brilliance, you get to publish with top cited scientists, and that, so in a sense, your collaboration with them is a result of your brilliance. However, the consistency with which we observe, the results that we observe, and the statistical significance suggests that option 1 is the most plausible, although we cannot rule out option 2. So our results strongly suggest that indeed publishing early on in your career with a top cited scientist has career altering consequences. However, it is important to stress that this doesn't mean that basically success is just achieved through this collaboration, right? Of course, this is about being in the right place at the right time, publishing with the right people, and making the most of it. So of course, it's not just enough to publish one paper with a top cited scientist and then the rest of your career is basically plans itself out. Of course, you have to still be very good. However, what our results suggest is that still there are career altering consequences to publishing a paper like that early on in your career. And also, if you recall, let's say a key message was that the biggest relative difference was worth seeing for people that do not have early career excellence across a number of dimensions. So our suggestion here is that it could be especially game-changing to favor collaboration with top-cited scientists for those people who may not be starting their career in the best conditions, for instance, not in top institutions and so on. So access to top scientists should be made easier, or at least that's one of the main conclusions that we can draw from our analysis. Let me now quickly jump to part number 2 of my talk, where, like I said, I want to look at disciplines now and see how unequal or mobile are the academic ranks of these disciplines. So here we look at a much larger data set. So here we are looking at 57 disciplines according to the Web of Science classification that cover 4 large areas. So disciplines in the life sciences, physical sciences, social sciences, and technology. Again, here we look at people with at least 10 career years. And here in particular, we are interested in seeing what happens between the first 5 and the second 5 career years. Here we place much fewer restrictions on the rate of publication. So overall, we end up with a sample, with a pool of over 5 million authors. And the key part here is that the analysis that will follow will take place at the level of cohorts. So this means that we look at our data and we find in each discipline the people who started their career in the same year. So the people who start the career in the year 2000, in the year 2001, et cetera, et cetera. We look at what happens in the first 5 and in the second 5 years of these kind of groups, in these cohorts. And that's crucial because results would be very different if we didn't do that. So the rationale of looking at cohorts and how their careers evolve is that essentially cohorts are roughly people who start their career roughly in the same general conditions, and in a sense you could see them as competitors. Maybe that's a bit of a cynical view, but those are the people who will compete for the same readership, for the same, for instance, grant money during their career, so for the same resources at the end of the day. So what we do then in this paper is we look at first at mobility. So we rank people based on the impact they accrue, so the citations they accrue in the first 5 career years. And then we look at how this ranking has changed during the second 5. And we repeat that exercise for each cohort and aggregate the results. So here's an example in one of the disciplines. This is biotechnology. So here on the X and Y axis, we see basically we split each ranking into deciles, so from the top to bottom 10%. And the wherever you see darker colors, it means that people who started their careers in the first 5 years in that decile tend to remain in that decile. And when you see less dark colors, it means that these are rather unlikely jumps. So you see here that the darker colors are across the diagonal, meaning that on average, people tend to remain roughly around the same decile. And in particular, you see you see darker colors here, which is the top 10% of the ranking. So the darker color here means that people who start their career in the top 10% in terms of impact tend to remain in the top 10%. And the same applies at the bottom. So this square here is the bottom 10%. So the same consideration applies. So what we did is then we fitted a simple model on this, let's say, to capture mobility. In particular, this is like a random walk model where Pij is the probability that starting from a certain decile I, you will move to another decile j in the following 5 years. And d here plays, so this delta square is effectively your movement, your displacement in the ranking, and d, which is the parameter that we estimate by fitting, is effectively the equivalent of the diffusion coefficient in a random walk. So here, for instance, is the what we get basically after fitting. So we get an estimate for d, so that's a proxy for mobility. So the higher d, the higher mobility is in a field. And this is what this particular discipline, biotechnology, would look like if, let's say, mobility would follow exactly our model. And this is the difference between the random walk model and reality. And you see that more or less this model does a good job, except for the very top and the very bottom. So here we have quite significant differences, right? So most of the mobility is well captured. So you see here, the colors are not so dark, but again, the model essentially doesn't capture just the bottom and top 10% of these rankings. So we decided to take a look at those deciles, and what we found is that essentially there is pretty systematically this kind of deviation. So this is a picture of precisely this quantity, so the deviation from model and reality aggregated over all of our disciplines, and we see that more or less the mistakes that our model makes is stable. So this is for every year and every discipline. This is for the top 10%, and this is for the bottom 10%. So you see that more or less our model, our very simple model, captures mobility well and systematically makes, let's say, the same mistake throughout history. However, this is a very aggregate picture, and the deviation between our model's prediction and reality change a lot in certain fields. So for instance, in chemistry, the deviation between our model and reality has increased a lot over the years when it comes to the top 10% and decreased a lot in the bottom 10%. Conversely, in genetics, we see an opposite trend. So the deviation follow, basically in the top and bottom 10% follow completely different patterns. So each discipline has its own history, but if you aggregate, you see pretty much this stability. Then we want to see what's the relationship between mobility and inequality of a field. And the reason we do that is that because in the social sciences, typically when you look at countries where you have a very strong inequality, for instance, in terms of wealth and income, tend also to be very societies where there is very little social mobility. So here we wanted to see if the analogy was there also when looking at disciplines instead of countries, and when replacing our D, our parameter D, as an indicator for mobility, and the standard Gini index as the indicator for inequality. So that tells you how unequally distributed are the citations in a given field across all the authors in that field. So here the good news is that at the level of an aggregate picture, so here pulling together all disciplines, we see that mobility has increased and inequality has decreased over the years. I should stress that these results are obtained at the level of cohorts. The picture would be very different if we looked at the data differently. But again, here's some positive news. So there's an increase in mobility. So over time, it has become easier for early career researchers to climb the ranks of their disciplines, and overall inequality has decreased. And then we tested this relationship at the level of individual disciplines. So in this plot, each dot is a single discipline in a single year. And here you have our estimator of mobility, and this is the Gini index. And you see that there's a pretty clear negative relationship, which tells us that those disciplines in which there is a higher inequality, so in which the distribution of citations is more concentrated into a smaller number of authors, those are harder to climb. So mobility is lower, whereas those disciplines where citations are given more equally across the population of authors are more mobile and easier to climb. So what are the conclusions here? So this one is essentially what I just said. So there is a negative relationship between the, let's say, the ease with which you can climb the ranks of a discipline over the first few years of your career and how unequal the discipline is. But, and in general, I would say there are good news here. So what we saw is that there is this negative relationship in general, but then we can look at an aggregate picture, and in the aggregate picture, we see mobility increasing and inequality decreasing. And again, this is at the cohort level. Things would be very different if we didn't pool researchers in cohorts, but instead if we took a look at the overall population. So for instance, if you make these plots where every year you don't look at cohorts, but you look at the entire population of authors active in that year, regardless of their seniority, then you would see that inequality has actually increased starting from around the year 2000 and quite significantly. There are differences in patterns, but this is what you would see. So it makes a big difference how you organize the data. We think that it makes sense to look at cohorts for the reasons I explained, but things will be different with other assumptions. And another important conclusion is that what we saw is that a simple random walk model explains a lot of the mobility in the rankings. And what we see is that basically just the top and bottom parts of the ranking are kind of frozen, meaning that if you start there, you tend to stay there. And this, again, is similar to what we see in social mobility in the social sciences. This is an observation actually made by the famous Italian economist Pareto more than 100 years ago, when he first observed that most of social mobility in a country takes place in the middle strata of the income distribution, and people who are at the top, so those who are extremely rich, and people who are at the bottom, so the very poor. Those are the only strata of the population that do not experience much social mobility and are kind of frozen. So there are interesting analogies between our results and results from the social sciences and what they can teach us about mobility and inequality in a completely different context. So I will stop here, and these are the two papers that basically correspond to the two halves of my presentation. One was published in 2019. The other one is very recent. It's a preprint that we put online a couple of months ago. And this is basically all the people I am collaborating with in, let's say, this broad research area. So a lot of them were not in the two papers I have presented, but you still learn a lot by collaborating with a bunch of different people. So I feel like I should acknowledge all of them. And in particular, I should acknowledge the two main driving forces between the two papers I have presented. Weihua Li, who was the first author of the first paper, is not at UCL anymore. He has moved back to China. And Ye Sun, who is currently my postdoc, she's the first author of the second paper I talked about. And with that, I will acknowledge the funding bodies that made this research possible and stop here. And hopefully there's plenty of time for discussion. Thank you very much for your attention.
Thank you. Thank you very much for this very interesting talk. And if there's any question from the audience, just feel free to unmute yourself. So first, if I may, I have a question myself
Sure.
about the first part of the basically the first paper, the collaboration with the top scientist.
Mm-hmm.
So I'm thinking. So the result is that basically, as an early career researcher, if you can get access to some top scientists, and you will be really benefit from this collaboration, making a high possibility that you will also become a top scientist in the field. So I'm considering that because this is the result that data suggests. I'm considering thinking of the mechanism that lead to this result. So what I can think of course, there are two possible reasons, or in the reality might be the combination of the two. So first of all is if you have the connection with top scientists, he or she may guide you in a certain way, making you your ability increasing. And the other reason might be that you are joining the network of the top scientists. So in the end, you also benefit in terms of the citation. Of course, I think in the end, the result will be, the reason will be the aggregation of both. But is it possible to distinguish like which reason contributes more to the final result? For example, if
So,
yeah.
Yes and no, in the sense that the second reason that you mentioned can be measured, and we did, in the sense that it's these two dimensions that we looked at here. So when we did this analysis where we looked at pairs of people, so what we saw is that those that get to write, to co-author a paper with a top-cited scientist get more access repeatedly and more frequently to other top-cited scientists throughout the rest of their career. So that's exactly the network effect that you probably had in mind. So you start interacting with top scientists, and that naturally facilitates the interaction with other top scientists. And of course, that has an impact. Concerning the first point, like I said, so people have looked, and we are also looking at mentorship relationships. So relationships where we can, let's say, where there is ground truth data that tells you that this pair of collaborators are a mentor-mentee pair. And we are, I don't have results yet, but we are trying to see how these results generalize to that context. The big limitation being that it's very hard to get that kind of data. So you don't get big samples. So that's the reason why it's a bit difficult to fully disentangle the two effects. Now, of course, it's undeniable that if you get to collaborate with someone who is at the top of their field, they will, I mean, that will be helpful in a number of ways, including becoming better at writing impactful papers. So obviously there is a learning process here that I don't think can be captured just from publication data. You probably would need interviews or something like that. So go and ask people what did they learn from their supervisors, their mentors, and their collaborators.
Yeah, actually, I'm thinking of the other possibility is that is it possible to remove the contribution of to remove the contribution of citations from the paper that the person co-authored with the top
Oh,
scientist.
yeah.
So
Absolutely. Yeah. I forgot to say that, but like this is all cleaned. So it's we removed all the papers published early on, and not just early on with let's say at least with the person responsible for the co-authorship with, let's say, with the top scientists that you publish early on in your career. The effect is still very much there. So the effect is very robust. So no matter what you do, it is there. It is a bit stronger or a bit weaker, depending on what you control for, but it is always there. Then, of course, if you leave there the contribution coming from that paper or other papers that you may have published with top people, then of course the effect is much bigger. But even if you remove that, you can still, let's say, if you want to put it like that, it's still statistically significant.
Okay, thank you very much.
Thank you.
Any other questions? So I have a general comment because I don't know this area of research very well. Now maybe the results showed in this presentation is mostly the direct analysis from the data. What the data suggests this result or the increase of inequality of this result. And it's possible to study the mechanism or to propose some possible mechanism that lead to this result. Because in the end, if we want to change something, if we want to change the inequality, if we change some structural problem, if there is any spotted by problem from the analysis of the data, we may need to understand what really caused these problems, and then we can solve it.
I mean that's the $1 million question, I guess. So I guess an important point, which I didn't say but should have said, is that like this is all a consequence of the fact of whether you accept or not that impact should be measured via citations in one way or another, with some manipulation, some index, etc. But as soon as you accept that, then I don't think there's much we can do. That like these kind of results are very consistent throughout. There's plenty of studies that show inequalities, and there is a very simple reason why you see inequalities. Like the very root is, for instance, think of search engines. When you look for like papers in a certain area on Google Scholar, for instance, those are ranked not just in terms of citations. There's a relevance there based on your input, but mostly, I mean, the papers you see at the top are usually highly cited papers. And that makes sense because that means that many other people found them useful, but also reinforces the problem, right? And the same applies at the level of people. So if you are highly cited, then chances are that the next time you apply for a grant, people will take your reviewers will take the fact that you are highly cited as a very good sign, etc. So you are likely again to be funded again, etc., etc. So the reinforcement mechanisms are there, and I think are pretty strong and probably unstoppable, and they are similar to just all the mechanisms that generate inequalities in societies. I think that the real question is whether we should measure impact just with these numbers. And personally, I don't think so. So one of the main reasons to do this kind of work was to illustrate what happens if you take a relatively narrow view of what academic impact is and just measure it with numbers. Then you say, okay, there is a lot of predictability here based on just the first few career years. Does that make sense? My personal view is that it does not make a lot of sense, and that scientific impact is much more than just numbers. And that also ties to your initial question. So let's say you are an early career researcher. Should you go fishing for the best collaborators Depends on what you want to do. So if you want to optimize your citations, that's probably a good idea, but that doesn't necessarily mean that that's the best thing for you. I mean, you may become a much better scientist overall throughout a different career path.
Yeah, thank you very much. I think this is a very interesting discussion in the sense that, for example, when I was an undergraduate, some professor would say that you should only publish the good result, a good paper. You don't do a lot, like 10, 20 papers per year, but you only do and focus on the very important question. You may doing that for 10 years without any paper, but afterwards you may do some real contribution to the society, to the community. But from the perspective of citation or academic career, actually, I don't think this is a good strategy in terms of, only if you are in the system, you can continue to do the research. If not, then you don't have a
Actually, I have a paper about that too. So if it's not published yet, but there's a preprint. And what we looked at is the difference between impact and innovation. There are scores that measure how innovative or disruptive a paper is. And what we saw is that after long stretches of time where people don't publish or publish much less frequently than they used to, that's when they produce their most innovative work. Now, the problem is that, and I have another paper on that too coming up, innovation and impact are two very different things. So not very highly correlated. So I think what your advisor was telling you was very good advice if you wanted to produce very innovative research. And again, but with the important caveat that high innovation doesn't necessarily get rewarded with high citations and vice versa. So there are all these factors to consider. Like, I don't have a strategy to suggest. I think all I can do is tell you what we see in this data, but I don't have. If I could go back in time, I don't think I wouldn't know what to do anyway. So
yeah, thank you. Sylvia?
that's it. Yeah.
Hi. Thanks for the very interesting talk, first of all. And second, I was thinking maybe it could be interesting to show, if it's possible, maybe with a model, I don't know, what would happen if you introduce the fact that more people can have co-authorship with these top scientists. Maybe what happened to the, I don't know, to their trend in time and stuff like that. Have you think about that? Do you think it's feasible to do
No,
something else?
I mean, certainly possible. So off the top of my head, the problem I would see in building a model would be that at some point you would have to, let's say, take a position on the chicken and egg problem, right?
Yeah.
So how do you see things? Do you think that collaborating with a top scientist will cause higher success, or is it the other way around? You are brilliant and therefore you get to collaborate with highly impactful people.
You don't know this causality between the two measures.
No, like our results are all of a correlational nature. Again, all I can say is, I mean, after you see correlation after correlation after correlation, you start thinking that there must be some causality here. So that's the point I was trying to make. But yeah, no, we haven't thought about a model here. At the level of data, I guess you could say something by specifically selecting, looking at the impact in a career. Let's say somebody who maybe couldn't start their career in a highly prestigious institutions, etc., and then later on in their career they get to publish with someone who is highly visible, because at the end of the day, it's visibility, and see if that has a measurable impact later on in a career. That would definitely strengthen the argument that we made in the paper that access to top scientists should be facilitated in one way or another.
Yeah, I see. Thank you.
Thanks.
Is there any other questions? And so if there's no other questions, I think we can stop this seminar here. And Giacomo, thank you very much to bring this presentation to us. Very interesting result. And actually for me, this is a very kind of new area of actually knowing what happened around us, which is, I think, is very, very interesting.
Yeah.
And later I will post this recording of this talk on YouTube. And thank you everyone for coming. I hope to see you in 2 weeks.
Thanks a lot for having me. It was a pleasure. Thanks.